All right, what I'm going to talk about next are Taylor series. And I say get to because Taylor series are really cool. They're a super powerful result that typically you don't hear about until you get Calculus 3. But really, we know enough at this point to get a pretty good idea of what a Taylor series is and start to see some of the really cool applications of them. So first, big picture. When I talk about Taylor series, or maybe you'll hear the term Taylor polynomial, the idea is to take a function, any function you want, and I guess not really any function you want, but any function that would be relevant to us. And what you want to do is approximate it with a polynomial, because generally polynomials work really nicely. If you open up a given quiz, regardless of what section we're in, if the function that I give you is a polynomial, you're probably a lot happier than if you see some product with logs or exponentials or trig functions or some sort of function composition. Generally, polynomials work out really nicely, so it makes sense that we might want to find a polynomial that, loosely speaking, best fits a given function. So what I'm going to do is I'm going to demonstrate that problem with this function f of x equals the natural log of x plus 2. The natural log of x plus 2 kind of has this shape right here. Maybe you're picturing the graph of the natural log of x, which has this vertical asymptote at 0 and goes through the point 1, 0 before kind of leveling off. Let's see, I guess it should attain a height of 1 when my x value equals e, so it's not drawn perfectly, but whatever. The graph of natural log of x looks more like what you see in blue, and this is a function transformation shifting the graph 2 units. The graph of the natural log of x plus 2 is what's pictured in purple in front of you. What I want to do is come up with a polynomial that looks as much like this graph as possible. And specifically what I want to do is have my polynomial look as much like this graph as possible when x equals 0. I want to focus on x equals 0. You could focus on a different x value, but to keep things as simple as possible, let's focus on x equals 0. So how are we going to create this polynomial? Well, it kind of depends. It depends on how precise you want to be, right? Because polynomials can have as many terms as you want. A third degree polynomial, for example, might look like f of x equals x cubed plus, 2x squared minus 5x plus 1. But I could also build a 10th degree polynomial, 2x to the 10th power minus 9x to the 9th plus 7x to the 7th, so on and so on. Maybe it follows logically that the more complicated polynomials with larger degree, will be able to more closely mimic this graph when x equals 0. And simpler polynomials with lesser degrees, won't have the flexibility to be able to approximate this graph quite as well. So you're like, great, just pick a polynomial with a really high degree. Well, then our work gets harder. So there's sort of this balance, right? I don't want my polynomial to be too big, because then it's going to be really hard to figure it out. But I don't want my polynomial's degree to be too small, because then it won't do a great job of approximating the function that I'm trying to approximate, the natural log of x plus 2. Let's start with the simplest polynomial possible, something that you might not even think of as a polynomial, a 0-degree polynomial. So a 0-degree polynomial might be so simple that this actually feels kind of complicated, but let me try to talk you through what we'd be doing. If you have a 0-degree polynomial, that polynomial is just equal to some constant, some number right here. C0 or C0 is meant to represent some constant. And I have to figure out what constant that should be equal to if I want this polynomial, T0 of x, or T0, to best approximate my function f of x when x equals 0. So since f of x is equal to the natural log of x plus 2, I can figure out what f of 0 is equal to. It would just be the natural log of 0 plus 2, in other words, the natural log of 2. So then I come over here and consider my polynomial, t0 of x. t0 of x is just equal to some constant, c0. I want to figure out what that constant should be. And in order for this polynomial to best approximate this function when x equals 0, I want the height of this polynomial to be the same as the height of this function when x equals 0. The height of the function when x equals 0 is the natural log of 2. The height of the polynomial when x equals 0 would be t0 of 0. In other words, copy exactly what you see up here, changing all the x's into zeros. Well, there are no x's to change into zeros, so I just get c0. The height of the function in orange is always equal to whatever constant we put in place of c0. So what constant should we put in place of c0? Well, we want the height of the function to be the same as the height of the polynomial when x equals 0. And the height of the polynomial when x equals 0 is the natural log of 2. So what that tells us is c0, this constant, has to be equal to the natural log of 2. If I want the 0-degree polynomial that best approximates this function when x equals 0, that 0-degree polynomial, which I'll denote t0 of x, should be equal to the natural log of 2. Natural log of 2 is some number that's like 0.7 something. So this polynomial, which is really just a constant function, will always have a height of the natural log of 2, that 0.7 something. That's what's pictured right here in orange. The function that I'm trying to approximate is pictured in purple. The polynomial that I'm trying to approximate it with is pictured in orange. Good news and bad news. At the point where x equals 0, these two curves have the exact same height. That's good. But if I gave you these two pictures and I was like, hey, I'm trying to approximate the graph in purple with the graph in orange, did I do a good job? You'd be like, nah, not at all. They don't look anything alike. I mean, sure, they have the same height at x equals 0, but that's kind of where the similarities end. If you want a graph that looks more like the graph in purple, you're going to need a more complicated polynomial. A 0-degree polynomial ends up just being a horizontal line, and a horizontal line is not going to look a whole lot like this function that we have pictured in purple. So we're going to need to move on to a more complicated polynomial. Maybe instead of a 0-degree polynomial, a polynomial that's just equal to some constant, we should consider a first-degree polynomial, a polynomial that's equal to some constant times x plus some constant. I'll take advantage of some kind of logical naming conventions and call this new polynomial, this first-degree polynomial, t1 of x instead of t0 of x. Because t1 of x is a first-degree polynomial, I have a little bit more freedom in terms of how I define it. There's two different numbers that I get to choose. I get to choose the constant term and the coefficient on the x term. So what should I choose those two values to be? Well, remember my goal is to still approximate this function f of x equals the natural log of x plus 2 for x values near 0. So I still want to make sure that the height of the function in purple when x equals 0 is the same as the height of the function in red when x equals 0. That's this first statement. So since f of x is the natural log of x plus 2, I have to think about f of 0, which as we saw above is the natural log of 0 plus 2, in other words, the natural log of 2. And I have to construct my polynomial t1 of x, which remember is equal to some constant, I don't know which one yet, times x plus some other constant, in such a way that the height of this polynomial will be the same as the height of this function when x equals 0. I know the height of the function when x equals 0. Let's figure out the height of the polynomial when x equals 0 by changing all the x's into zeros. Nice thing happens because this is a polynomial. c1 times x is c1 times 0. That completely goes away. The height of this polynomial when x equals 0 is just equal to c0. Wait a minute, that's exactly what happened up here, right? The height of the function at 0 is the natural log of 2, and the height of the polynomial at 0 is my constant term, c0. Adding on another term, this first degree term, does not affect the height of the polynomial when x equals 0. So if I want the height of the function when x equals 0 to be the same as the height of the polynomial when x equals 0, I still need c0 to be the natural log of 2. I need this to equal this. But as we saw up here, that's not enough. We want to use our linear term to make the polynomial in red look more like the polynomial in purple when x is equal to 0. What does it mean to look more like the polynomial in purple? Well, maybe we'd want the first derivatives to be the same, right? That would kind of make sense. If the slope of the graph in purple at x equals 0 is the same as the slope of the graph in red when x equals 0, then these two graphs will look more similar. So not only do I want their heights to be the same when x equals 0, I want their first derivatives to be the same when x equals 0. If f of x is the natural log of x plus 2, f prime of x is 1 divided by x plus 2 times the derivative of x plus 2, which is just equal to 1. So f prime of x is 1 divided by x plus 2. I don't want the slope of this function generally. I want to know the slope of this function when x equals 0. So I change all the x's into zeros, and I get 1 divided by 0 plus 2, in other words, 1/2. The slope of the tangent line to the function at x equals 0 is 1/2. I want to figure out how to make the slope of the tangent line to this polynomial at x equals 0 also equal to 1/2. Well, what I would do is I take the first derivative of this polynomial, t1 of x. Fortunately, derivatives of polynomials are really easy, and I can take the derivative here. Might look a little bit weird without numbers in place, but remember this is just a constant, so its derivative goes away, and this is a constant times x, so the derivative is just c1. Really what I want is not the slope of the tangent line to the polynomial at any x. I want the slope of the tangent line to this polynomial when x equals 0. So what I gotta do is change all the x's in this expression into zeros. But there are no x's in this expression, so t1 prime of 0 is just equal to c1. I want f prime of 0 to equal to t1 prime of 0, so I want c1 to be equal to 1/2. What I'm saying is the first degree polynomial that best approximates this graph in purple is the polynomial 1/2 x plus the natural log of 2. And that polynomial is what you see pictured in red here. Note that when x equals 0, these two functions have the exact same height, just like we saw up here in orange. But now, not only do they have the same height at x equals 0, they also have the same slope at x equals 0. So all of a sudden, the graph in red is looking a lot more like the graph in purple. It's still not great, though. I mean, nobody would confuse these two graphs, right? They look very different. For example, the one in purple is curved, and the one in red is linear. But maybe if we considered a more complicated polynomial, instead of a degree 1 polynomial, maybe we should consider a degree 2 or quadratic polynomial. Generally, a second degree polynomial is some constant times x squared plus some constant times x plus some constant. We're still trying to approximate f of x equals the natural log of x plus 2. It's just now we're going to do so with the second degree polynomial, so maybe it makes sense to call it t2 of x, which will be some constant times x squared plus some constant times x plus some constant. First things first, I got to make sure these things have the same height when x equals 0, so I have to make sure that f of 0 is equal to t2 of 0. Well, f of 0, as we've seen a few times now, is just the natural log of 0 plus 2, in other words, the natural log of 2. And t2 of 0, because this thing is a polynomial, if I change all the x's into zeros, it's just going to be equal to the constant term, c0. The exact same thing it was equal to in this case, and the exact same thing it was equal to in this case. And maybe you can see how no matter how big I make my polynomial, whether it's a second degree, third degree, 100th degree, no matter how many terms I have in here, the height of the polynomial when x equals 0 will be completely determined by my constant term right here. So I don't need to keep doing this analysis in the first line. In order for f of 0 to be equal to t2 of 0, I need c0, my constant term, to be equal to the natural log of 2, regardless of the degree of the polynomial. And similarly, since we need the first derivative of the function to be the same as the first derivative of the polynomial, I consider f prime of x, which as we saw before was 1 divided by x plus 2, and t2 prime of x, which we can calculate pretty easily as 2 times c2 times x plus c1, treating all the c's as constants and taking the derivative using the power rule. I need f prime of 0 to be the same as t2 prime of 0. As we saw above, f prime of 0 is 1 divided by 0 plus 2, in other words, 1/2. And t2 prime of 0, a cool thing happens. If I change all the x's into zeros, this term completely goes away. The slope of the tangent line to this polynomial when x equals 0 is completely determined by this coefficient c1. t2 prime of 0 is equal to c1. For the slopes to be the same, I need c1 to be equal to 1/2, the exact same conclusion that I came up with up here. And what's really cool is even if I have a 50th degree polynomial, when I take the derivative, the constant term will go away. The term that started out with the first degree will now be a constant term, and all the other terms will have an x in them. And when I change the x's to zeros, all the other terms will go away. The point that I'm making is when I look at polynomials that are more complicated than degree 2, I don't need to do these first two lines of analysis. It's not a coincidence that I came up with the same answers here as I came up with here and I came up with here. That's always going to happen going forward, and that'll cut down the work that I need to do significantly. Really, all that I needed to figure out here to try to make the polynomial curve at roughly the same rate that the function curves is take their second derivatives at 0 and set them equal to each other. None of this work was necessary. All I had to do is figure out the second derivative of x and the second derivative of t2 of x. Let's see, the second derivative of x would just be the derivative of the derivative. The derivative of 1 over x plus 2, maybe you could think about that as x plus 2 to the negative 1 power. So if I use the power rule here, I bring the negative down in front, and then I got x plus 2 raised up to the negative 2 power, and then I multiply by the derivative of the inside function, which is just 1. What I end up with is negative 1 divided by x plus 2 squared. So the second derivative of this function, negative 1 divided by x plus 2 squared, needs to be evaluated at 0. Copy exactly what you see here, changing all the x's into zeros. You get negative 1 divided by 0 plus 2 squared, in other words 2 squared, in other words 4. What about the second derivative of my polynomial? Well, the second derivative is just the derivative of the derivative, and I have the derivative written right here, so it's pretty easy to figure out. Just take the derivative of this thing. This is a constant, so it goes away. 2 times c2 is a constant serving as a coefficient, so I leave that completely alone, take the derivative of the x, which is just a 1, and I get 2c2 as my answer. Really, it's not the second derivative at x that I'm interested in. It's the second derivative at 0 that I'm interested in. So I change all the x's into zeros. But what you see is there are no x's over here. So the second derivative evaluated at 0 is just 2 times c2. I need the second derivative of the function to be the same as the second derivative of the polynomial. So I need negative 1/4 to be the same as 2c2. In other words, c2 should be equal to negative 1/8 if I multiply both sides of this equation by 1/2. If I want the second degree polynomial that best approximates the graph in purple, I would call it t2 of x, and its equation would be negative 1/8 x squared plus 1/2 x plus the natural log of 2. This polynomial is what you see pictured in green right here. And maybe you're starting to see how it's kind of starting to fit the graph in purple, especially at x values close to 0. Let's go through this process one more time. Let's figure out a third degree polynomial that best fits this function in purple. Well, let's see. We'd certainly want the heights of the function and the height of the polynomial to be the same, so f of 0 should be the same as t3 of 0. We want their slopes when x equals 0 to be the same, so the first derivative of the function at 0 should be the same as the first derivative of the polynomial at 0. And this idea that I loosely talked about up here as the curve was really making sure they have the same concavity. To make sure they have the same concavity, I want the second derivative of the function at 0 to be the same as the second derivative of the polynomial at 0. But if I have a third degree polynomial here, I can do even better. I can make the third derivative of the function at 0 the same as the third derivative of the polynomial at 0. My function f of x is still the natural log of x plus 2. If I want the function to have the same height as the polynomial at 0, I could go through the analysis that we did on these two lines, which is the same as the analysis we did on these two lines, which is the same as the analysis we did on these two lines. But maybe you can see how we wouldn't even have to do that, because when x equals 0, all of these terms go away, and I'm left with just c0. What I'm saying is to ensure that the function has the same height as the polynomial when x equals 0, I still need c0 to be equal to the natural log of 2. And to ensure that the function has the same slope at 0 that the polynomial does, I still need c1 to be equal to 1/2, as we calculated up here, and we also calculated up here. If I want the function in the polynomial to have the same second derivative at 0, I know that c2 has to be equal to negative 1/8, as I calculated in this previous iteration. So really the only calculations that I have to do as I move into this third degree polynomial is make sure that the third derivative of the function at 0 is the same as the third derivative of the polynomial at 0. What's the third derivative of the function? The third derivative of the function is the same as the derivative of the second derivative. The second derivative is negative 1 divided by x plus 2 squared. In other words, negative x plus 2 to the negative second power. So the third derivative will be the derivative of negative x plus 2 to the negative second power. If I'm taking this derivative, I use the power rule. I bring the negative 2 down in front. Negative 1 times negative 2 gives me positive 2. I leave the x plus 2 completely alone, and then subtract 1 from the exponent to get the negative third power. Not done. I have to multiply by the derivative of the inside part using the chain rule here, but that's just equal to 1, so I guess I am kind of done. The third derivative of this function is just 2 times x plus 2 to the negative third power. In other words, 2 divided by x plus 2 cubed. What about the third derivative of my degree 3 polynomial here? Well, let's see. My degree 3 polynomial is some constant times x cubed plus some other constant, negative 1/8 specifically, but I'll just leave it general for now, times x squared plus some other constant, 1/2, but I'll leave it as c1 for now, times x plus some other constant, the natural log of 2. When I take the first derivative of this polynomial, this goes away. I end up with 3 times c3, this constant, x squared, plus 2 times c2, this constant, x, plus c1 plus 0. The second derivative is just the derivative of that derivative. 3c3 is all a constant. I bring the 2 down in front. I get 6c3 times x plus 2c2. But I don't want to stop there. I want to take the third derivative of this polynomial. This is all a constant, so it goes away when I take the derivative. This is some constant times x, so the derivative is just 6c3. Remember, my goal is to make the third derivative of the function at 0 equal to the third derivative of the polynomial at 0. The third derivative of the function is 2 divided by x plus 2 cubed, So the third derivative of the function evaluated at 0, I copy exactly what I see here, changing all of my x's to zeros, and I get 2 divided by 2 cubed, in other words, 2 divided by 8, in other words, 1/4. The third derivative of my polynomial is equal to 6c3. Technically, it's the third derivative of the polynomial evaluated at 0 that I'm interested in. So I change all the x's into zeros, but this is just a constant term. So there's no x's to change into zeros. I get 6c3. In order to make the third derivative of the function the same as the third derivative of the polynomial, I need 1/4 to be the same as 6c3. If 1/4 equals 6c3, and I divide both sides of this equation by 6, I get that c3 should be equal to 1/24. My third degree polynomial is made up of 4 different constants. 3 of them I already knew going into this analysis. The fourth one I just figured out is equal to 1/24. What I'm saying is if you want a third degree polynomial that best approximates the graph in purple, the polynomial that you would come up with is 1/24 x cubed minus 1/8 x squared plus 1/2 x plus the natural log of 2. And this polynomial is what's graphed in blue right here. It's not the most complicated polynomial in the world, it's just a third degree polynomial, but we already get a pretty good fit for this function. I mean, imagine if you zoomed in and just looked at this part of the picture right here. It's hard to even tell the difference between the graph in blue and the graph in purple inside of this blue box. The polynomial in blue does a great job of approximating the curve in purple, which is not a polynomial. Remember, it's the natural log of x plus 2, when I have values of x close to 0. This is the third degree Taylor polynomial, and it's our best approximation for the curve in purple. It's a lot of work that we've done in this video, but maybe I can make the argument that it's not that complex. I mean, imagine that we started out being like, all right, I'm willing to build a third degree polynomial, and I want it to best fit this function, the natural log of x plus 2. Well, I'd certainly want the height of the graph in blue to be the same as the height of the graph in purple. So I'd want f of 0 to be the same as t3 of 0. Changing all the x's into 0, I figure out that c0 is equal to the natural log of 2. But that's not enough. I'd also want their first derivatives at 0 to be the same. So I take the first derivative over here, I take the first derivative over here. Because this is a polynomial, when I take the first derivative, all of the terms except for 1 will still have an x in them. So when I evaluate that first derivative at 0, most of the terms go away, which is a really nice property of polynomials and allows me to figure out that this coefficient c1 should be equal to 1/2 the first derivative of the function evaluated at 0. And as long as I'm making the function the same as the polynomial at 0 and the first derivative is the same at 0, I might as well make the second derivatives equal at 0. And doing so tells me this coefficient, c2, should be equal to -1/8. And there's no reason to stop there. I might as well set their third derivatives at 0 equal to each other. And that tells me that c3 should be equal to 1/24. And you might be wondering why we're stopping here. Why not make their fourth derivatives equal at 0? Well, this is just a third degree polynomial. So when I take its fourth derivative, I just get 0 as the answer. Fourth derivatives and on don't contain any information when I have a third degree polynomial. If I had a fourth degree polynomial, I'd absolutely set the fourth derivative of the function at 0 equal to the fourth derivative of the polynomial at 0, but I don't. I have a third degree polynomial, so I stop right here. My polynomial is guaranteed to have the same height, first derivative, second derivative, and third derivative as this function at 0. And by having those commonalities, I end up with graphs that look really similar. I took you through all this in an iterative process. We first considered a 0 degree polynomial, then a first degree polynomial, then a second degree polynomial, and then a third degree polynomial. But really, we didn't need to do that. Really, what we should do is figure out what degree we want the polynomial to be, and then just do all the work in one. And that's what we're going to do in the next video, as we start to develop some formulas and some shortcuts for coming up with these Taylor polynomials.